Hello everyone. So in this chapter we are going to talk about solids and statics of the fluids. So there are four known states of matter: solids, liquid, gases, and plasmas. You're all familiar with the first three, but plasmas, which are systems of charged particles interacting electromagnetically, are in fact the most common. An understanding of the fundamental properties of these different states of matter is important in all the sciences, in engineering, and in medicine as well. So, forces put stress on solids, and stress can strain, deform, and break those solids, whether they are steel beams or bones. Fluids under pressure can perform work or carry nutrients and essential solutes, like the blood flowing through our arteries and veins. Flowing gases cause pressure differences that can lift a massive cargo plane or the roof of a house during the hurricane. High temperature plasmas created in fusion reactors may someday allow humankind to harness the energy source of the sun. In this chapter, you will be introduced to the basic properties of the three most common states of matter here on Earth. We will also talk about, more precisely, what the fluids are. We will talk about pressure. We will talk about how pressure changes at depth in a fluid. So as we change the depth, is the pressure changing or no? We will talk about Pascal's principle and buoyant force and Archimedes' principle. So we know from our everyday experience that the solid has a definitive volume and shape. Think about a brick, for example. The brick has a size and shape that is constant, meaning that the volume also of this brick is going to be constant until you apply force to it. A liquid has a definite volume but no definite shape. Imagine when you go to the gas station to fill out your tank in your car. The gasoline changes its shape of the original container in the gas station, wherever it is stored, to a shape of the tank in your car. But the original volume is unchanged. A gas does not have a definite volume or definite shape. It can flow. So gases are liquids, and liquids, they share many properties together. So all the matter consists of atoms or molecules. In a solid, the atoms are held together primarily by electric forces, and each atom is located at a specific position with respect to other atoms in the solid. These forces between these atoms are represented by these springs in a figure here. So this figure shows a model of portion of a solid. Atoms in solids are able to vibrate about their positions, similar to the balls that are attached to the springs in the model shown. At low temperatures, the vibrating motion is slight, and the atoms can be considered essentially fixed. There are two classifications of solids: crystalline, like these, and amorphous, like these. In crystalline solids, such as a quartz, shown in this photo here, the atoms have an ordered structure. Sodium chloride, which is a common table salt, is another example of a crystalline solid. The figure shows the sodium and chlorine atoms, which occupy alternate corners of the cube. In this figure here, the sodium atoms are represented by the large green spheres and chlorine atoms by small brown spheres. So these are the chlorine atoms and these are the sodium atoms. So as we said, this is a sodium chloride. In amorphous solids, such as glass, the atoms are arranged almost randomly And you can see that in this figure here. Liquid exists at a higher temperature than the solid state. The intermolecular forces in a liquid aren't strong enough to keep the molecules in fixed position, and they wander around in the liquid randomly, as you can see in this figure here. So this is a random motion of the molecule. Solids and liquids, they both resist compression due to their strong repulsive atomic forces. In gases, molecules are in constant random motion and exert only weak forces on one another. We will talk more about this in physics 2 when we study the thermal physics. The average distance between the molecules of a gas is quite large compared to the size of the molecule. Occasionally, the molecules collide with one another, but most of the time they move as nearly free, non-interacting particles. For this reason, gases can be easily compressed. And you studied this in chemistry already, or you will study this in chemistry, and we will study this in physics 2 when we study thermal physics. When the gas is heated to high temperature, many of the electrons surrounding each atom are freed from the nucleus, resulting in a collection of free electrically charged particles, negatively charged electrons, and positively charged ions. This state, with equal amounts of positive and negative charge, is called plasma. So in plasma, a long-range electric and magnetic forces mean that the charged particles interact with each other. Plasmas can be found inside the stars, in an accretion disk, around black holes, as shown in this figure here. Plasmas are much more common than solids, liquids, or gases because there are more stars around than any other form of celestial matter. So let's talk about density. Say you had two equal masses of aluminum and gold. One thing you would notice immediately is that the aluminum takes up over 7 times as much space as the gold. The way we quantify this difference is by using the concept of density. Density of the object having uniform composition is the mass of that object divided by the volume. So density is mass divided by volume, and units for density are kilogram per meter cube. So the density basically tells you how compact the object is, how much mass of the certain material in 1 meter cube you can fit right inside. The table shows the densities of some substances. The densities of more liquids and solids vary slightly with changes in temperature and pressure. For gases, the density vary a lot when the temperature and or pressure is changed. Under normal conditions, the densities of solids and liquids are about 1,000 times greater than the densities of gases. This difference implies that the average spacing between the molecules in a gas under such condition is about 10 times greater than in a solid or liquid. We can introduce another term. It's a specific gravity. The specific gravity of a substance is the ratio of its density to the density of water at 4 degrees Celsius. The density of water at 4 degrees Celsius is 1,000 kilograms per meter cube. So if we have a water at 4 degrees Celsius and we have a container that takes up 1 meter cube in volume, you can fill in 1,000 kilograms of water inside that container. So you see here, water is on this side of the table. Ice, you see how the density of ice reduces because ice is a crystallized water. So all the values in this table are at the standard atmospheric temperature and pressure, defined as 0 degrees Celsius and 1 atmosphere. 1 atmosphere pressure is 1.013 times 10 to the 5 pascals. Conversion from grams per cubic centimeters is you multiply by 10 to the negative 3. The force that is exerted by a fluid on an object when we immerse that object in a fluid is always perpendicular to the surfaces of the object, as shown in this figure here. The pressure at a specific point in a fluid can be measured with the devices similar to this one. This is an evacuated cylinder enclosing a light piston connected to a spring. The spring has been previously calibrated with known weights. When the device is submerged in a fluid, the fluid presses down on the top of the piston and compresses the spring until the inward force exerted by the fluid is balanced by the outward force exerted by the spring. If the F is the magnitude of the force on the piston, and A is the area of the top surface of the piston, notice that the force that compresses the spring is spread over the entire area. This gives us the way to define a pressure. So the pressure by definition is force per area. Units are for force, newtons for area meter squared. Newton per meter square is a Pascal, and we abbreviate that with PA. The English customary for the pressure is the pound per inch squared. Atmospheric pressure at sea level is 14.7 pounds per square inch, which is a standard unit, which in standard units is equivalent to 1.013 times 10 to the 5 pascals. So in English units, this is equal to 14.7 pounds per inch squared. So the effect of a given force depends on the area. If you have a 700 Newton man standing on a vinyl covered floor in regular street shoes, no harm comes to the floor, right? No harm comes to the man as well. But imagine she changes into golf shoes. The metal cleats on the soles can do considerable damage to the floor. With the cleats, the same force is concentrated onto a smaller area, which increases the pressure and can exceed the ultimate strength of the floor material, resulting in a damage of the floor. Snowshoes use the same principle, right? So the snow exerts an upward normal force to the shoes to support the person's weight. According to the Newton's third law, this upward force is accompanied by a downward force exerted by the shoes on the snow. If the person is wearing a snowshoes, the force is distributed over the large area of each shoe so that the pressure at any given point is relatively low and the person doesn't penetrate very deeply into the snow. So let's now consider a fluid in a container, such as water in a bucket. When a fluid is at rest in the container, all portions of the fluid must be in static equilibrium, which means at rest with respect to the observer. Also, all points at the same depth must be at the same pressure. Let's now imagine that this was not the case. Then fluid naturally would flow from the higher pressure region to the lower pressure region. Let's, for example, consider a small block of fluid like this one. This one here is filled with the fluid in this figure. So note that this fluid is not separate from the rest of the fluid. This is just to indicate a particular volume of the fluid. If the pressure were greater on the left side of the block than on the right, F1 would be greater than F2, and the block would accelerate to the right and wouldn't be in equilibrium, right? The block will accelerate in this direction. Let's now take a look at this figure here. The dark region, this one in the middle here, of the fluid is actually just a defined region within the fluid. This region has cross-sectional area A. Let's label that. And extends from the position Y1 to the position Y2. And it's below the surface of the liquid. So there are three external forces that act on this volume of the fluid. There is a force of the gravity, the upward force, this one here, exerted by the liquid below it, and this force, we're going to call it F2, is pressure of the fluid from below times the area, and the downward force, F1, which is equal to P1A, that's this force here, exerted by the liquid above this part here. P1 here is the pressure of this fluid on the top, and P2 is the pressure of this fluid at the bottom. Because the given volume of fluid is in equilibrium, these three forces must add to zero. So let's write that up. So everything pointing up is going to be positive, and everything pointing down is going to be negative. So what points up is P2A minus P1A minus mg is equal to 0. Now what we can do is we can rewrite this equation in terms of the density. If we know the volume of the container, and we know the density of the fluid, type of the fluid inside, we can calculate the mass. So by definition, density is mass per volume. So from here, mass is going to be density times the volume. The volume of this selected portion of the fluid here is going to be, by definition, volume is three-dimensional thing, right? So it's a surface area times how high this block is, right? So the volume is going to be surface area times y1 minus y2. Okay, let's put this back all into the first equation. So we have P2A minus P1A is equal to mass times G. So we're going to have G times, the mass is a density times the area V1 minus V2. We can cut out area is the common term in all three terms. So we have P2 minus P1 is equal to G rho Y1 minus y2. So notice that y1 minus y2 is positive because y2 is less than y1. So y1 minus y2 is greater than 0 because y2 is greater, because the magnitude of y2 is greater than y1. So the force P2 is greater than the force P1 by exactly the weight of the water between the 2 points. This is the same principle experienced by the person at the bottom of the pile-up in a football or a rugby match. Okay, moving on. So atmospheric pressure is also caused by piling up of fluid. In this case, the fluid is the gas of the atmosphere. The weight of all of the air from sea level to the edge of the space results in atmospheric pressure of 1.01 times 10, 1.013 times 10 to the 5 pascals at the sea level. We can use this to find the pressure at any depth below the surface of the water, as shown by this equation. So P is going to be equal P0, which is a atmospheric pressure, plus rho GH. From the previous slide here, we see that the pressure difference on this object here is equal to rho G y1 minus y2 is equal to h. How deep this part of the fluid is inside the big container. According to this equation, the pressure at depth h below the surface of a liquid open to the atmosphere is greater than atmospheric pressure by the amount of rho GH. This equation is called the equation of hydrostatic equilibrium. Also, this pressure is not affected by the shape of the vessels, as you can see in this particular figure here. This photograph, So this photograph here illustrates the fact that the pressure in the liquid is the same at all points lying at the same elevation. So all the points here, they have same pressure, or here or here. The shape of the vessel does not affect the pressure inside. So let's see how this relates to an example. The pressure at the bottom of the glass filled with water is P. The water is poured out and the glass is filled with ethyl alcohol. The pressure at the bottom of the glass is now smaller, equal, or larger than P, or it is indeterminate. So at a fixed depth, the pressure in a fluid is directly proportional to the density of the fluid, because we said that pressure is equal to P0 plus mgh, right? So the pressure at any depth is directly proportional to the mass, and from density is equal mass per volume. We see that the mass of the fluid is equal to rho v. So the pressure is directly proportional to the density of the fluid. Ethyl alcohol is less dense than water. So from here, we see that the pressure is going to be less than the pressure that water exerts, which in this case is going to be choice A. So because the pressure in a fluid depends on the depth and on the value of P0, which is atmospheric pressure, any increase in pressure at the surface must be transmitted to every point in that fluid. This phenomenon was first recognized by the French scientist Blaise Pascal, who lived from 1623 to 1662, and this is called a Pascal's principle. Pascal principles stress that the change in pressure applied to an enclosed fluid is transmitted undiminished to every point of the fluid and to the walls of the container. Important application of Pascal principle is in hydraulic press. As we can see here in this figure, we have a downward force, small downward force that is applied to a small piston of area A1 here. This pressure is transmitted through a fluid to a larger piston of area A2, creating this pressure on this side here, P2. As the pistons move and the fluid in the left and right cylinder change the relative height, right? So when we press on this side here, the fluid will move and it will be able to lift this heavy car here. So if we neglect these small differences, which mean we can say that fluid pressure on each of the pistons may be taken to be the same. So if we say that P1 is equal to P2, we end up with F1 over A1 is equal to F2 over A2. From the definition of the pressure, we can see that F2 is greater than F1 by the factor A2 divided by A1. So F2 is going to be equal to A2 over A1 times F1. So this is how the large load, such as car, can be moved on the large piston by a much smaller force on the smaller piston on the left side. Hydraulic brakes, car lifts, hydraulic jacks, forklifts, and other machines make use of this principle. Okay. So this figure here shows a simple device for measuring pressure, and this is called the open tube manometer. One end of this U-shaped tube containing a liquid is open to the atmosphere, and the other end is connected to a system of unknown pressure, P. This pressure, the pressure at point B, is going to be equal to P0 plus rho GH, where rho is the density of the fluid inside the tubing. The pressure at point B, however, equals to the pressure at point A, which is also known as pressure P. So we can conclude that P is equal to P0 plus rho H. The pressure P is called the absolute pressure, and the P minus P0 is called the gauge pressure or overpressure. I'm sorry, I keep writing pressure with lowercase p. So P minus P0 is called the gauge pressure. if the absolute pressure in the system is greater than the atmospheric pressure, H is going to be positive. And if the absolute pressure is less, which implies the partial vacuum, H is going to be negative, which means that the right-hand side of the column is lower than the left. On this figure here, we have another instrument that's used to measure pressure, and this is called a barometer. It's a mercury barometer. The barometer was invented by Evangelista Torricelli, who lived from 1608 to 1647. This is a long tube closed at one end and filled with mercury, and then inverted into a dish of mercury. The closed end of the tube is nearly a vacuum, so the pressure can be taken to be zero. It follows that P0 is going to be equal to rho GH, right? Because P is equal to P0 plus rho GH. If P is equal to 0, then we are going to end up with my rows look different. Where rho is the density of the mercury and H is the height of the mercury column. Please note that the barometer measures the pressure of the atmosphere, whereas the manometer measures the pressure of the enclosed fluid. So 1 atmosphere of the pressure is defined as the pressure equivalent of a column of the mercury that is exactly 0.76 millimeters in height at 0 degrees Celsius, with G defined as 9.80665 meters per second squared. Okay, let's write this out. I'm going to open the new page. 1 atmosphere is defined at the height of 0.76 meters at 0 degrees Celsius and with G equal to 9.80665 meters per second squared. At this temperature, mercury has a density of 13.595 times 10 to the third kilograms per meter cube. From these data, we can actually calculate the value for atmospheric pressure. So let's do that. P0 is going to be equal to rho GH. We have values for rho, for G, and for H. I forgot the 0 here. So when I plugged in this to my calculator, I got 1.013 times 10 to the 5 Pascal, which is equal to 1 atmosphere. It is interesting to note that the force of the atmosphere on our bodies, assuming the body area of 2,000 square inches, is extremely large, on the order of 30,000 pounds. If it were not for the fluids permeating our tissues and body cavities, our body would actually collapse. The fluids provide equal and opposite forces and that's why we are able to live. In the upper atmosphere or in space, sudden decompression can lead to serious injury and death. Air retained in the lungs can damage the tiny alveolar sacs, and intestinal gas can even rupture internal organs. So that's why it is a really important when you're diving at extremely deep depths that when you're coming up to the surface of the water, you have to, at every height that you emerge up, you need to stop to equalize the pressures and then continue, and that's why you're slowly coming up. You're not just suddenly decompressing. Okay, so let's see another example. We have several common barometers are built using a variety of fluids. For which fluid the column of fluid in the barometer be the highest? For mercury, benzene, water, or ethyl alcohol? So what do we know? We know that the pressure is fixed, right? So for the fixed pressure, the height of the fluid in barometer is inversely proportional to the density of the fluid, right? Because we know that P0 is equal to rho GH. So H from here is equal to P0 divided by rho G, right? So of the fluids, the one that is the least dense is the one that's going to produce the largest value for H. Okay, let's take a look. Where is the mercury? Mercury is here. Benzene is here. It's less dense, right? Water is 1000, so water is less dense than mercury but more dense than benzene. So for now, benzene is winning. And then ethyl alcohol is less than the benzene, so ethyl alcohol wins. This one will produce the highest value for H. Blood pressure is often measured using a specialized manometer, and I'm talking about how the blood pressure is measured before we invented these digital ones, right? The digital ones work at exactly same principle, right? So this specialized manometer is called sphygmomanometer, and it's illustrated in the figure here. So a rubber bulb forces air into a cup wrapped tightly around the upper arm and simultaneously into a manometer. The pressure of the cuff is increased until the flow of the blood to the brachial artery in the arm is stopped. Then a valve on the bulb is opened here, and the measurer listens with a stethoscope to the artery at the point just below the cuff. When the pressure of the cuff and brachial artery is just below the maximum value produced by the heart, the systolic pressure, the artery opens momentarily on each beat of the heart. At this point, the velocity of the blood is high and turbulent, and the flow is noisy, and it can be heard with the stethoscope. A manometer is calibrated to read the pressure in millimeters of mercury, and the value obtained is about 120 millimeters for a normal heart. As the pressure in the cuff is lowered further, intermittent sounds are still heard until the pressure falls just below the minimum heart pressure, which is a diastolic pressure. At this point, continuous sound is heard. In the normal heart, the transition occurs at about 80 millimeters of mercury. Blood pressure readings are usually expressed as the ratio of the systolic pressure to the diastolic pressure, which is 120 over 80 for the healthy heart. I hope this helps, and maybe you can use this slide to learn how to measure the blood pressure the old-fashioned way, using the stethoscope and actually listening to this. Okay, let's see how this is actually applied in an example. So if we have a blood pressure that's normally measured with a cuff of the sphygmomanometer around the arm, I'm sorry, this is a difficult word for me to pronounce. Suppose that the blood pressure is measured with a cuff around the calf of the leg of a standing person. The reading of the blood pressure will be the same here as for the arm. The less than it is for the arm, the greater than it is for the arm. Okay. So the answer here is that it is going to be greater than it is for the arm. Why is this? The blood pressure measurements in the cuff would be larger than the measured in the arm. If we imagine the vascular system of the body to be a vessel containing a blood, the pressure in the liquid in the blood will increase with depth. The blood at the cuff is deeper in the liquid than at the arm, and it is at a higher pressure. The blood pressures are normally taken at the arm because it is approximately at the same height as a heart. If blood pressures at the cuff were used as a standard measurements, the adjustments would need to be made for the height of the person, and the blood pressure would be different if the person were standing or laying down. So this is one of the reasons every time you measure the blood pressure, your arm has to be kind of at the level of your heart. Okay, let's talk now about the buoyant forces and Archimedes' principle. Archimedes' principle said that an object completely or partially submerged in a fluid is buoyant up by the force with magnitude equal to the weight of the fluid displaced by the object. So in this case here, what we have net upward force is the buoyant force acting on this object submerged in the water. For example, to lift someone if you're both standing in a swimming pool is much easier than lifting the same person on dry land. Water provides partial support to any object placed in it, and its upward force is called a buoyant force. The physical case of the buoyant force is the pressure difference between the upper and the lower sides of the object. So let's take a look at the figure here. The fluid indicated by the darker color is pressed on all sides by the surrounding fluid. The arrows indicate the forces arising from the pressure. Remember that the pressure increases with the depth, so the arrows on the bottom are larger than on the top. Adding them all up, the horizontal components cancel, but there is a net force upward because these forces are larger than these forces. This force, due to differences in pressure, is called a buoyant force. So, since the sphere of this water neither rises or falls, the vector sum of the buoyant force on the force and the force of the gravity on the sphere must equal to 0. So basically what we're going to have here, we have mg down here and the buoyant force up here. So from here it follows that the buoyant force is equal to mg, where m is the mass of the displaced light blue fluid with the sphere of the dark blue fluid. Now, if we imagine replacing the sphere of water with, for example, a cannonball in this figure here, this only changes the mass on which the pressure acts. So the buoyant force is going to be the same. It's going to be equal, B is equal mg, where m is the mass of the displaced fluid, not the mass of the cannonball. The force of gravity on the heavier ball is greater than it was on the fluid, so this is the reason why cannonball is going to sink. The heavier objects in the water are going to sink because mg is greater than the buoyant force. And buoyant force is directly proportional by the mass of the displaced fluid. So basically it is directly proportional to the mass of this light blue fluid that was in this space here, that was displaced from that point because the cannonball took that space. So we can also obtain Archimedes' principle using this figure here. This is the same figure which we used to talk about how the pressure varies with depth, right? So horizontal forces from the pressure cancel because whichever horizontal force from the pressure from the left is equal in magnitude but opposite direction from the right. So they're going to add up to 0. But in the vertical direction, P2A, which is a force, we call that force F2, acts upward on the bottom of the block of fluid, and P1A and the gravity force of the fluid act downward. We're going to call this F1. They act downward. The buoyant force is the result of the difference in pressure and is equal to the magnitude of the weight of the displaced fluid. This buoyant force is same no matter what material is occupying the volume because it is due to the surrounding fluid. So you can put here fluid, you can put steel, you can put iron. The buoyant force here is always going to be the same. And this buoyant force is due to this fluid that's surrounding this object here, due to this light blue fluid. So the buoyant force is acting up is equal to mass of the displaced fluid times g. And that is equal, we have P2A acting up minus P1A acting down. So the buoyant force is going to be equal to the density of the displaced fluid times the volume of the displaced fluid times g, where the mass of this fluid that's displaced is equal to rho times the volume. So this is a mass of displaced fluid. So this result applies equally to all shapes because any irregular shape can be approximated by a large number of infinitesimal cubes that we can put inside the fluid. Okay, so now let's see what happens with buoyant forces and how Archimedes' principle is applied when we have a totally submerged object. I have no idea why I have this twice, so I'm just going to delete this here. So if we have a totally submerged object in a fluid of density rho of the fluid, the upward buoyant force acting on the object has a magnitude that is given by what? The buoyant force is going to be mass of the displaced fluid times g. So that is going to be equal to the density of the fluid times the volume of the object times g. So when I go back one slide, here we said the volume of the fluid because this was fluid, right? But this here is the volume of submerged object. Okay, fix this. It's just that in this particular example here, we had a fluid as a submerged object. Okay, if the object has density rho of the object, the gravitational force acting on the object has a magnitude that is given by what? The gravitational force, W, is equal to mg, which is equal mass is the density of the object times the volume of the object times g. So what do we have here? We have two objects here on this example. A totally submerged object that is less dense than the fluid on the figure A, and on the figure B, a totally submerged object that is denser than the fluid. We know that the denser objects are going to be heavier objects and they're going to sink, and a object that is less dense than the fluid will actually float or start coming up. So for the object that is less dense than the fluid in which it is submerged, the net force is going up, and the heavier objects are going to sink. The net acceleration is pointing down, and if acceleration is pointing down by the second Newton law, the net force is pointing down. Okay, so let's now write just net force. That force is going to be, we have a buoyant force that acts up, and we have a weight of the object that pulls down. So that is going to be equal to, in both of these terms, let's write it out actually. Fluid volume of the object times g minus density of the object, volume of the object g. So we see here that the volume of the object and g are the common terms. So in the first part of the equation, we have density of the fluid, and then minus density of the object. So this equation tells us that if the density of the object is less than the density of the fluid, the net force exerted on the object is going to be positive and upward, like in the figure A, and the object accelerates upward. If the density of the object is greater than the density of the fluid, the net force is going to be downward, and the object is going to sink, is going to accelerate downward. So this equation is the reason why the heavy objects, more dense heavy objects, sink than the light objects. This is the reason why you don't use a piece of steel as a floaty, but rather you use a piece of, I don't know, rubber that is filled with air, like in those flamingos that we are using to float in the pools during, well, we are all using to float in a pool during the summer. Let's now talk what happens with the floaties, right? Floaties are partially submerged objects in static equilibrium that are floating in a fluid, as shown in this figure here. The upward buoyant force is balanced by the downward force of gravity that is acting on the object, right? Same as before. Buoyant force is going to be density of the fluid times the volume of the object. This is mass of displaced fluid times g. The weight of this object, which is Fg in the figure here, is equal to mass of the floaty times g, which is rho times the volume of the object times g. Because the two forces are equal in magnitude in opposite direction is a condition for the floaty to float on the surface of the water. Basically, what we have is B is equal to Fg. So this is a condition for floating. What are we going to end up with? We're going to end up with what? Rho of the fluid, volume of the object, times g is equal to density of the object times the volume of the object times g. Oh, I'm sorry, I made an error here. This is displaced fluid is volume of the fluid here times g. So this is going to be fluid. Displaced fluid. So from here, we are going to see that the ratio for the volume of for the density of the object to the ratio of the density of the fluid is going to be equal to the volume of the fluid displaced to the volume of the object. So let's think about some real-world examples of this. Under normal circumstances, the average density of a fish is slightly greater than the density of the water. So a fish would sink if we didn't have a mechanism for adjusting its density. A fish changes the size of the internal swim bladder so it can maintain neutral buoyancy as it swims to various depths. The human brain is immersed in a fluid called the cerebrospinal fluid, which has a density slightly less than the average density of the brain. This means that most of the weight of the brain is considered by the buoyant is supported by the buoyant force of the surrounding fluids. All right, let's see other applications of the buoyant forces and Archimedes principles. The first figure here, this one, shows a common device that's used to check the antifreeze in a car radiator. The small balls in the enclosed tube vary in density so that all of them float when the tube is filled with pure water. None float in pure antifreeze, and one float in a 5% mixture, 2 in 10% mixture, and so forth. The number of the balls that floats is a measure of the percentage of antifreeze in the mixture, which in turn is used to determine the lowest temperature the mixture can withstand without freezing. Okay, in the second figure here, we have an example of charged and discharged car battery, right? The degree of charge in some of the car batteries can be determined with so-called magic dot process that is built into the battery, as shown in this figure. Inside a viewing port in the top of the battery, here, the appearance of an orange ball indicates that the battery is sufficiently charged. A black dot indicates that the battery has lost the charge. So if the battery has lost the charge, the orange ball will move out, and then you will just see the black space here. If the battery has sufficient charge, the density of the battery fluid is high enough to cause the orange ball to float. As the battery loses the charge, the density of the battery fluid decreases and the ball sinks beneath the surface of the fluid, making the dot appear black. Okay, let's take a look at some concept questions here. Atmospheric pressure varies from day to day, as we all know. The level of a floating ship on a high pressure day is lower, higher, or different than on a lower pressure day. I am going to say it's C, no different than on a low pressure day. Why is this? The level of floating of a ship is unaffected by the atmospheric pressure. The buoyant force results from the pressure differential in the fluid. For the floating object, the ratio of the densities of the object and fluid is equal to the ratio of the volumes of the object and the fluid. So on a high pressure day, the pressure at all points in the water is higher than on a low pressure day because water is also incompressible. However, the rate of change of pressure with depth is the same, resulting in no change in a buoyant force. All right, let's take a look at another one. The density of the lead is greater than the density of the iron, and both are denser than water. Compared to a solid iron object of the same dimensions, the buoyant force acting on a solid object is greater, equal, or less. So since both lead and iron are denser than water, both objects will be fully submerged and will displace equal volumes of water. Hence, the buoyant forces acting on the two objects will be equal. Let's take a look at another one. A glass full of water sits on a scale. If you hold your finger in a water without touching the glass and without spilling any water, what happens to the reading of the scale? The reading of the scale is going to increase because by submerging my finger in the water, I'm going to create more pressure on the water, which will create more pressure on the scale, and the scale reading is going to increase. Okay, so let's take a look at another one. Which of the following statements is not true? each of these statements is about pressure. So we are looking for the statement that is not correct. Okay, so the pressure in a liquid is due to the weight of the column of the water above. Yes. The pressure exists everywhere in the liquid. Yes, it does. The pressure increases as the depth increases. Yes, it does, because pressure is rho GH. At the particular depth, the pressure depends on the shape of the container. Does it? No, it doesn't. So that's the one. And the pressure is exerted equally in all directions at any point. Well, we're going to have, due to the buoyant force, it's going to be mass of the displaced fluid times G. Displaced fluid times G, right? So it may not be exerted equally in all directions at any point. It is exerted equally in the lateral directions in any point, but on the vertical, no, it doesn't, because we have a buoyant force that acts upward. So this one is not correct. Okay, let's now look at some examples. First one, we have a balloon that's filled with helium. The mass of the balloon material is 3.2 kilograms and the density of the helium is 0.179 kilogram per meter cubed. If the balloon is a sphere with a radius of 4.9 meters, what is the maximum weight that it can lift? So we are basically looking at the maximum cargo weight that the balloon can lift. Okay, so what are the things that we know? We know that the balloon is a sphere of the radius of 4.90 meters. We know that the density of the balloon, which is filled with the helium, is 0.179 kilograms per meter cube. We know that the mass of the balloon is equal to 3.20 kilograms. What else we know? Balloon is flying in the air, so the density of the air is 1.29 kilograms per meter cube. Okay, what else do we know? We know that the density is by definition mass divided by the volume. What do we have? You have a balloon in the air, so it's going to experience a buoyant force up, and when you put the cargo, it's going to be m of the cargo times g down, right? So what do we know? We know that the maximum amount of cargo the weight of the maximum cargo is going to be equal to the magnitude of the buoyant force, right? Okay, in order for balloon to lift this up, right? Okay, so the buoyant force is equal to what? Mass of the air displaced times g. which is what? Volume displaced times the density of the air times G. The displaced volume is equal to the volume of the balloon. So every time balloon takes space in the air, is going to displace that much of the air, volume of the air, right? Okay. So what? The buoyant force here is going to be equal to the density of the air times the volume of the balloon. It's a sphere, so it's a 4/3 PR cubed, and then times G. When I plug this into my calculator, I ended up with the maximum buoyant force. The buoyant force is 6,236 newtons, which is equal to the maximum weight that it can lift. Okay, I don't know what I did. All right, that's that. All right, let's take a look at another example. Okay, so we have a bargain hunter that purchases a gold crown at a flea market. After she gets home, she hangs it from the scale and finds that it weighs a 7.84 newtons. She then weighs the crown while it is immersed in water, and now scale reads less, 6.86 newtons. The question is the crown made of gold? So what are we going to do here? So this is we're going to apply, we have a figure here, so we're going to apply Archimedes' principle to the submerged object. So the goal is to find the density of the crown, and then we're going to compare the density of the crown to the density of the goal. So we already have the weight of the crown in air, so we can get the mass by dividing it by the acceleration of gravity. If we can find the volume of the crown, we can obtain the desired density by dividing the mass by this volume. And when the crown is fully submerged, the displaced water is going to be equal to the volume of the crown. This same volume is used in calculating the buoyant force. So our strategy is as follows. Apply Newton's second law to the crown, both in the water and in the air, to find the buoyant force. Then we use this buoyant force to find the crown's volume, and then divide the crown's scale weight in air by the acceleration of gravity to get the mass. Then we know the mass and we know the volume, we can get the density of the crown. Okay, so the first part is we know that the weight in the air is equal to 7.84 newtons, and we know that weight in the water is equal to 6.86 newtons. So the free body diagram is here on the picture. When we have a crown suspended from the scale in the air, we have a tension here is going to be equal to the weight, right? So it is at static equilibrium. So the first part in the air, what do we have? We have it is at equilibrium, so 0 is equal to tension in the core in the air minus mg. So from here, mg is equal to tension in the air, and m is equal to the weight divided by g. So this weight of the object in the air actually is equal to the tension provided on the scale. Okay, So the mass here, if I divide 7.84 by 9.80, I ended up with a mass to be 0.800 kilograms. So now when the crown is immersed in the water, the scale reads 6.86 Newton, but we have a weight force of the crown that points down, and we have a buoyant force due to the water. The crown is going to be in static equilibrium, so then we have another second Newton law equation. 0 is going to be equal to what? Tension, which is a weight of the water, minus the weight of the crown, and then plus the buoyant force. So this weight of the water is actually tension on the scale when immersed in the water. Okay, so from here we know that the weight of the crown is equal to the tension in the air. So we have 0 is equal to weight of the water minus tension weight in the air plus buoyant force. So from here we can calculate a buoyant force, which is going to be equal the difference in these two tensions, right? So the buoyant force, when I calculate it here, is going to be equal to 0.980 newtons. Okay, so now we know that the buoyant force, by definition, is equal to the mass of the displaced fluid times g. Okay, so the mass of the displaced fluid is equal to the volume of the displaced fluid, which is water, times the density times g. The volume of displaced water is going to be equal to the volume of the crown. Okay, so we have a density of the water, we have g, we have a buoyant force, so from here we can calculate the volume of the displaced water, which is equal to the volume of the crown, is going to be equal to the buoyant force divided by the density of the water times g. When I plug in my values, I ended up that my volume is equal 1.00 times 10 to the negative 4 meter cubed. Okay. I know what is the weight of my crown in the air, so I can calculate the mass of the crown is the weight in the air divided by g. So that is going to be 7.84 divided by 9.80. We already calculated this to be 0.800 kilograms. Okay, we know that the volume of the displaced water is equal to the volume of the crown. So now we can calculate the density of the crown is going to be equal to the volume of the crown divided by the mass of the crown. When I plug in, the volume is 1.00 times 10 to negative 4 meter cubed divided by the mass of the crown. I end up with the density 8.00 times 10 to the third kilograms per meter cube. The density of the gold is equal to 19.3 times 10 to the third kilograms per meter cube. So the crown is either hollow, made of alloy, or it is both, but it's definitely not a gold. Okay, let's take a look at another example. If we have a raft that is constructed of wood having a density of 6 times 10 to the second kilogram per meter cube, the surface area is 5.70 meters squared, and the volume of this raft is 0.600 meters cubed, then the raft is placed in fresh water so that it's partially submerged, right? To what depth is the bottom of the raft submerged? Okay, there are going to be two forces acting on this raft. We're going to have a buoyant force acting up, and there's going to be a weight of the water, of the raft acting down. Because raft is at equilibrium, the sum of these two is going to be equal to 0. The buoyant force depends on the submerged volume, and the volume that is submerged is going to be equal to the area times how deep it is submerged. Okay. So what do we have? The raft is at equilibrium, so we know that the buoyant force minus mass of the raft times g is equal to 0. So then from here we know that the buoyant force is going to be mass of the raft times g. Okay. The buoyant force, by definition, is equal, so this is from second Newton law, buoyant force by definition is displaced water, displaced fluid, times g, right? So that's going to be equal to what? Mass of the displaced water is going to be density of the water times the volume of the displaced water, and then times g. Volume of the displaced water is the surface area of the raft times h. So then the buoyant force is going to be equal to density of the water, volume of the displaced water is equal to the volume of the raft that is submerged, and that's equal to surface area times h, and then times g. Okay, so now when we plug this in to my second Newton law equation, I end up with rho of water area times h times g is going to be equal to the weight of the raft, which is mass of the raft times g. We don't know the mass of the raft, but we know the density and the volume of the raft. Okay, so that's going to be equal to the density of the raft times the volume of the raft times g. So from here If I want to solve for h, that's going to be equal to g and g are going to cancel out. So that is going to be equal to volume of the raft times the density of the raft divided by the volume of the water, density of the water displaced times the surface area of the raft. When I plugged in these values, I ended up with the height that is submerged in the water is equal to 0.0632 meters. Okay, that is it for this chapter.